Okay, now we have derived the Henderson-Hasselbalch equation, and we will be using that equation whenever we have a buffer problem. So let's do a pretty simple example of a Henderson-Hasselbalch problem, and hopefully give you a sense of how to think about it from an intuitive sense instead of it just being some equation that you plug things into. So you need to know the Henderson-Hasselbalch equation. You have to memorize it. But here it is, right? pH equals pKa plus log of the conjugate base over the acid. Okay. Now, let's think about this equation a little bit. We said in the previous video that these concentrations represent the two types of soldiers that are present in our buffer. The conjugate base going to react with any acid in salt, and the weak acid would react with any base in salt. Now, if you look at this equation as a whole, you can say, well, the pH of any particular buffer equals some constant. This constant is related to the equilibrium constant of the acid. How good of an acid is it, right? If it has a high Ka value, that means it's a better acid. This number will be lower, and the pH of the buffer will be lower. That makes sense. Better acid, lower pH. But this is a constant for a particular combination of acid and conjugate base. Now, the rest of this is not a constant. It's dependent on this ratio of base to acid. Okay. So one way to think about the Henderson-Hasselbalch equation and the pH of a buffer is to say, well, if I had a completely equal buffer, I had an equal concentration of base as I do acid, then the ratio of the two will be 1. The log of 1 is equal to 0, and the pH of my buffer is just going to be equal to the pKa. That's a great way to think about the Henderson-Hasselbalch equation with any problem that you're looking at. If you have an equal amount of each type of soldier, then the pH of that buffer is just equal to the pKa. Now, what if you don't have an equal amount equal concentration of both components? Well, then the pH of your buffer is going to be shifted one way or the other from the pKa. So let's put more conjugate base than we have acid. If there's more base than acid, then this ratio is going to be greater than 1. The log of something that's greater than 1 is a positive number, and then therefore the pH of this buffer is going to be greater than the pKa. We're going to add some positive number to the pKa, and that makes sense, right? If we have a buffer that has more base than acid, then that pH is going to be increased, right? More basic. And the opposite's true too. If we have more acid in our buffer than base, then this ratio will be less than 1. And the log of something that's less than 1 is a negative number. So we'll be subtracting away from that pKa value, which means the pH of our buffer will be less than the pKa value. Again, that makes sense. More weak acid than base, your pH is going to be lower. Now, what this also means is that it doesn't really matter what the pKa is for your acid that you're using in your buffer. You can have the pH of that buffer equal whatever you want. Let's say the pKa of my buffer, or the pKa of my acid was 2, and I wanted a buffer that was a pH of 7. Well, the pKa is very different than the pH, but as long as I added a ton of base and hardly any acid, I could have the pH of my buffer go all the way up to 7. Now, it turns out that this ratio would have to be 10,000 to 1, which is not ideal for a buffer, because what it would mean is you have a bunch of one type of soldier and hardly any of the other type, which means this buffer would be really good at dealing with acids, because it has a lot of conjugate base soldier, but it would be terrible with dealing with bases because you got hardly any of this weak acid in there. So even though you can make any pH buffer you want from any weak acid, it's best to use an acid that has a pKa close to the pH which you want. If the pH of your buffer is close to the pKa, that means this ratio of acid to base is close to 1, which means you got about equal concentrations of both types of soldiers, so it's a really versatile buffer. Okay, but remember, that's how we think about Henderson-Hasselbalch equation. If I had an equal amount of acid and base, then the pH of that buffer is just going to be equal to pKa. If that ratio is off one way or the other, then we're going to add or subtract from the pKa. So let's look at a question and just try to do a little calculation and then see if this logic works out. Okay, what's the pH of a buffer composed of 0.1 molar acetic acid and 0.085 molar acetate? Okay, well, here's our acetic acid. Let's try this out. The acetic acid is, I'm going to click down here. Boink. Acetic acid is 0.1 molar. Whoop, that's supposed to be an M. And the acetic acid is the acid in this problem, or in this buffer. Acetate is the conjugate base, which is 0.085 molar. Okay. We're also told that the Ka of this acetic acid is 1.8 times 10 to the negative fifth. Now don't make a silly mistake and plug this number into your Henderson-Hasselbalch equation. Remember, it's the pKa, not the Ka. So if we take the negative log of 1.8 times 10 to the negative fifth, we get something like 4.76. Now, once we have this number, we can use our basic understanding of Henderson-Hasselbalch and say, well, if I had an equal concentration of acetate and acetic acid, then the pH of my buffer would be 4.76. Now, we know that we don't have an equal amount of each of these. We've got a little more acid than we do base. And so what does that mean? It means that this ratio is going to be a little less than 1. I'm going to be subtracting a number from the pKa, so the pH is going to be less than 4.76. We can calculate it really easy just by plugging stuff in. pH equals 4.76 plus the log. Don't get these things backwards, right? It's base over acid, so whatever units you have for these concentrations will cancel out as long as the units are the same. These could be moles, it could be molar. As long as they're the same, they're going to cancel out. Okay, so we've got our pKa, and let's look. The log, let me do it on my calculator, 0.085 divided by 0.1 is 0.85. I take the log of that, and I get negative, what do I get? Let me write it down. Negative 0.0706. So I'm subtracting this number from 4.76. And so my final pH is 4.69. Okay? Always look at your answer and see if it makes sense. We've got a buffer with this pKa. It's got a little more acid than base, and so my pH should be a little more acidic. It should be a little less than 4.76. That's it. Okay. Now the next video is going to show a much more complicated Henderson-Hasselbalch, where we're going to have to do a little more work to find out what these values are that we're putting in the Henderson-Hasselbalch. But always remember, a great way to start thinking about it is if the concentrations of these components are the same, then the pH of the buffer is equal to pK.